Welcome back to Exposure Stories. California, the blazing land of America's west coast, is facing one of the most persistent and destructive enemies in its modern history: drought. Rivers that once flowed year-round have shrunk into fragmented channels, reservoirs reveal ghostly shorelines, and fertile farmland has fractured into red, lifeless dust. Climate change has intensified heat waves, shortened rainy seasons, and disrupted snowfall patterns that once sustained the state's vast water system. Faced with these realities, California could no longer rely on nature alone. A bold and controversial idea emerged: pull billions of liters of water from the Pacific Ocean, push it deep into the mainland, construct massive desalination plants along the coast, recycle wastewater at unprecedented scales, and link everything through an immense network of pipelines and aqueducts stretching hundreds of kilometers. Together, these technologies aim to resurrect land that once seemed beyond saving. This is not science fiction, but a quiet engineering revolution unfolding in real time. Join Mandarin Tech as we uncover how California is fighting the greatest water crisis in its history with some of the most advanced infrastructure on Earth. If California were a country, its economy, worth more than $3.5 trillion would rank as the fifth largest in the world. More importantly, its agricultural sector feeds not only America but much of the global market, producing roughly one-third of the United States, vegetables, and nearly two-thirds of its fruits and nuts. Almonds, grapes, lettuce, tomatoes, and citrus grown in California reach dinner tables across continents. Yet this agricultural giant depends on an uncomfortable truth: nearly 80% of all human-used water in the state is consumed by agriculture. The irony is striking. California, despite its wealth and productivity, is naturally water-poor. Geographically, it sits between the cold Pacific Ocean and the towering Sierra Nevada mountains, which form a natural barrier that blocks much of the ocean's moisture from moving inland. Rainfall is heavily uneven, with the northern regions receiving far more precipitation while the south endures semi-desert conditions. For decades, the state depended on one fragile lifeline: snow. More than 60% of California's natural water supply historically came from snowpack in the Sierra Nevada. Each winter, snow accumulated meters deep, acting as a frozen reservoir. As temperatures rose in spring and summer, that snow melted gradually, feeding rivers, reservoirs, and aqueducts over many months. This slow release was perfectly timed for agriculture and cities alike, but that cycle is now breaking down. In drought years, snowfall has dropped by 20 to 60%, and what snow does fall melts weeks earlier than expected. Instead of a steady flow, water rushes off too quickly or evaporates under rising temperatures. Scientists now estimate California is experiencing its worst drought in at least 1,200 years. Iconic reservoirs such as Shasta, Oroville, and Meade have fallen to around 40% capacity or lower, exposing cracked earth and abandoned infrastructure. Waiting for mountain water was no longer an option. California had to look elsewhere. That elsewhere was the Pacific Ocean, vast, relentless, and nearly limitless. But seawater carries a major problem: salt. At roughly 3.5% salinity, seawater is toxic to crops and unsafe for human consumption. Removing salt requires enormous energy and precision, which is why desalination was once considered impractical at large scales. Advances in membrane technology, energy recovery systems, and high-efficiency pumps changed that equation. Along California's coastline, giant desalination plants began to rise, each capable of converting millions of liters of seawater into fresh water every day. The process starts offshore, where massive intake pipelines, often 2 to 3 meters in diameter, are installed on the seabed. Made from carbon steel or high-density polyethylene, these pipes are designed to resist corrosion, crushing pressure, and violent ocean currents. Heavy-lift cranes lower each section into place, weld them together, and anchor them firmly to the ocean floor. Seawater is drawn from hundreds of meters offshore to reduce contamination and protect marine ecosystems. Intake screens prevent large debris and sea life from entering the system, while powerful pumps pull in tens of thousands of liters per minute. Even so, seawater arrives full of sediment, organic matter, and microscopic particles. Inside the plant, the water undergoes multiple filtration stages. Gravity-driven sand filters trap suspended solids, while chemical treatments using disinfectants and coagulants cause fine particles to clump together and settle. Cartridge filters with pores as small as 1 micron remove nearly everything visible under a microscope. Only then does the water reach the heart of the operation: reverse osmosis. Reverse osmosis is a battle against physics itself. Salt ions cling tightly to water molecules, and breaking that bond requires immense pressure. High-powered centrifugal pumps force seawater through ultrafine membranes at pressures approaching 60 bar, about 60 times normal atmospheric pressure. These membranes allow only water molecules to pass while rejecting salt, bacteria, and contaminants. The water is often sent through a second reverse osmosis stage to remove trace ions and achieve ultrapure quality. The result is nearly perfect freshwater. Before distribution, the water is remineralized with calcium and magnesium, its pH is carefully balanced and its taste restored. Stored in massive tanks, this water is then pumped into municipal systems or sent directly to agricultural regions. While desalinated water is expensive, often costing 2 to 4 times more than traditional sources, it offers something priceless: reliability. Yet desalination alone cannot sustain California. Long before seawater entered the picture, the state launched one of the largest water infrastructure projects in human history. It begins high in the Sierra Nevada, where dams such as Shasta, Oroville, and Folsom capture snowmelt and rainfall, forming colossal reservoirs capable of storing tens of billions of cubic meters of water. From these reservoirs, water flows into two vast systems, the Central Valley Project and the State Water Project. Their backbone is the California Aqueduct, a nearly 700-kilometer artificial river that slices through valleys, deserts, and mountain passes. In some regions, massive pumping stations lift water more than 600 meters uphill, consuming enormous amounts of electricity. Reinforced concrete pipelines and canals branch outward, delivering water to cities, industries, and some of the most productive farmland on Earth. This infrastructure reshaped California's destiny. Regions that were once arid scrubland became fertile agricultural centers. The Central Valley, now one of the most productive farming regions in the world, supplies more than 1/3 of America's vegetables and 2/3 of its fruits and nuts. Fields that once depended entirely on unpredictable snowmelt gained access to year-round irrigation. Crop yields soared, rural economies flourished, and California became an agricultural superpower. But this success came at a steep price. Construction costs reached tens of billions of dollars, while annual maintenance and energy expenses continue to rise. Water prices for households and farmers have increased, reflecting the true cost of moving every cubic meter across such vast distances. Recognizing that freshwater sources alone were insufficient, California also turned inward toward its cities. Wastewater recycling became a cornerstone of modern water security. Every drop from toilets, sinks, showers, and industries flows through underground sewer networks into massive treatment plants. The process begins with mechanical bar screens that trap plastics, rags, and debris. Grit chambers remove sand and gravel, while primary settling tanks allow heavy organic matter to sink into sludge. In aeration tanks, billions of microorganisms consume remaining organic pollutants, forming activated sludge that cleans the water biologically. The partially purified water then passes through microfiltration membranes that block bacteria and parasites, followed by reverse osmosis systems similar to those used in desalination. The final product is astonishing: water so pure it rivals distilled water. After disinfection and mineral adjustment, this recycled water can be used for agriculture, industrial processes, groundwater replenishment, or even direct human consumption. These facilities not only supply additional water, but also reduce pollution entering rivers, lakes, and the ocean. By reclaiming wastewater, California ensures that no drop is wasted in a state where every liter matters. Today, California's water system is no longer dependent on a single source. It is a vast, interconnected network that blends mountain snowmelt, desalinated seawater, and recycled wastewater into one resilient supply. Existing aqueducts now connect coastal desalination plants with inland reservoirs and farms, allowing water from the sea and mountains to flow through the same arteries. This hybrid system represents the future of water security in a warming world. It is expensive, complex, and energy-intensive, but it works. Against relentless drought and an uncertain climate, California is not waiting for rain. It is engineering its survival drop by drop, proving that even in the driest conditions, human ingenuity can keep the land alive.